My name is Maxence. I was a former student in mathematics, and today I'm going to talk about feature selection and importance. So the goal of feature selection.
Hello.
Hello.
Hello, guys. Yeah.
Hi everyone. Sorry about that. I encountered some trouble to connect. So let me, Maxence, maybe do a proper intro.
Yeah.
All right. So thanks for coming, all of you, and yes, to begin with, Happy New Year. So today is a bit a special event in the sense that, okay, it's a bit late for Hong Kong. I know it's a bit early for Abu Dhabi. But so it's a joint session between Abu Dhabi and Hong Kong, but actually we would have like speakers that are not from the local community. So one speaker, Maxence, comes from France, and the other one, Yann, that will do the second talk, will come from the US. So today the session is really focused on feature importance and selection. So to give you a broad idea, if you are not that advanced in machine learning, I would say, when you do modeling, if you have garbage in, you have garbage out. So the whole goal of feature selection and importance is to think and devise methods to see what are the relevant inputs to put in your model. And actually, this is very important just to do proper modeling, but also to understand what are the models doing and their impact in, I would say, real life. So if you were to use more and more like this kind of models in the everyday life, impacting the life of millions of people, you want to understand what the models are doing, how they react, and you want to troubleshoot them in case they make poor decision to fix them or to counter their decision. So that's in this sense that all this feature importance and selection is important, and it has ties to broader and more like high-level area like fairness or bias against like cultures and against certain populations. So that's why I thought it's interesting to have this topic this evening. And basically that's it. The program for tonight is like first talk for the 45 or so minutes and questions. It will be Maxence that will present such methods. And then the other talk, like in 1 hour, it will be Yann from the University of Washington, which is working in a top lab on this field. And those guys are known to have brought Shapley values to the machine learning world that will go deeper into and maybe abstracting a bit all this method to show a unifying network. And I think that's it for the core meet for tonight meetup. For the people in Abu Dhabi, since it's the first one, maybe I will, after this first meetup, introduce maybe more what's the vision, what do we want to do, what can we learn together. So for those that want to stick, I will blabber a bit after these two talks on this kind of initiative and what we will do after COVID. For the others, I don't think it's super important or what you can go back to your occupation or your night. So that's it for the program. So for introducing Maxence quickly. So Maxence studied in the UK. He studied then a master that I also did like a couple of years ago on applied mathematics and computer vision, which I would say is the top master in France for learning such things. You will learn a lot from professors that are well known in this area. I would say this master is more mathematics oriented than practical, but nonetheless very high quality. And after that, Maxence did an internship in BNP Paribas, so a French bank, where he studied problems around the supply chain, which was quite topical during this COVID crisis with all the supply chain with China breaking and then with other parts of the world. And I guess he did some feature selection there too. So with further ado, I will let Maxence present what he knows and what he wants to share with us on feature selection and importance. Maxence, it's all yours now.
Okay, thank you, Gauthier. Yeah, so today I'm going to talk about feature selection, and I'm going to quickly explain why we do feature selection. So to start, the first thing here that motivates feature selection is interpretability. As Gauthier said, we want to understand the models we are using. So the fact to include many unimportant features in the learning models is not a good thing, because it negatively impacts the interpretability. It makes the model less easy to understand. Also, the actual accuracy of the model can be improved by wisely selecting features. And lastly, the complexity of the model is also very an important feature, because it usually is grows linearly with the number of features, and for the training step, the complexity grows linearly, and for the computation of the actual prediction, it is the same. It usually at least linearly depends on the number of features. So I'm going to start through the presentation. I'm going to use a well-known data set for spam and non-spam detection. Is collected by an employee of HP in 1999. So the goal is to predict binary variable equal to 1 if the email is a spam, equal to 0 if the email is not a spam. We have 57 features and 4,601 emails that we split in two for a training set and a test set. And I'm going to use a base model to compare with more subtle model where I perform the feature selection. So for this particular task, logistic regression is well adapted, because it's a binary classification, and this model is well adapted for binary classification. So we assume that the log odds of an email being a spam depend linearly on its features. And there is a latent variable where equal to the linear combination of the features plus a logistic random variable epsilon that follows logistic regression with mean 0 and variance 1. And that's it. This model can be fitted by maximizing the observed likelihood that is expressed in the second part of this slide. And so when training this model on the data set, on the training set that I mentioned, we obtained a good accuracy on the training set and the test set, and we can see the absolute value of the coefficients. That gives us a first idea of which features should be important and should be included in the model. But we'll see later that the feature importance is actually quite different when we use other methods than just blindly training a model and just looking at what features has the biggest coefficients and define their importance accordingly. So we start with some basic methods. The most obvious method when you tackle such a task would be to look at the correlation of the features with the target variable. So here there are three possible cases. First, if the feature and target are both continuous, we compute the usual correlation between these variables, which is expressed in the formula. If the feature and target are categorical, then we can perform a chi-squared test to check if both variables are independent or not. That is that if the two variables are independent, we expect that the number of observations where X is equal to category E and Y is equal to category J should be equal to EIJ, which is the observed number of observations where X is equal to I and multiplied by the average number of proportion of observations where Y is equal to J. Then we compute the distance between this expectation and the actual observed values of that is the count of observations where X equal I and Y equal J. And under the null hypothesis of no correlation, this test statistics follow a chi-squared law with I-1 times J-1 degrees of freedom, and we can reject it with reject the null hypothesis with the significance level that we chose. This is for when both variables are categorical, and this is the case that I actually used for this data set. Since features are continuous and target is binary, we can compute point biserial correlation, which is defined there and which is very useful to compare the correlation of continuous variables with a given target that is binary. So here I show some the 20 most important features according to point biserial correlation. This is the first step in choosing features. And I show the test accuracy. There's the number of features removed when I remove the least important features, obviously. So here we see that removing doesn't impact the test accuracy for the very least important features, but start decreasing starting from 13, 14 features removed. So a good choice would be to remove 14 features, which is that it doesn't impact much the test set accuracy, whereas the training set is not impacted either. A second basic method that can be used for feature selection is recursive feature elimination. The idea is to train a base model again with feature importance output, such as logistic linearization, where the feature importance is given by the absolute value of the coefficients, decision tree, where the position of nodes, where the variables intervene gives us a proxy for this variable's importance. We inductively remove the least important features and retrain the model with the subset obtained and repeat the operation until we reach we satisfy some condition or we reach some threshold. So on the span dataset, removing features one by one, while the important value, the absolute value of the ratio of the least over the most important feature is below a threshold. This is a stopping condition. Works well. We see that we can remove up to 18 features without impacting set accuracy too much. So this is already slightly better than just looking at correlation. And the stopping criteria here that I chose is that I want the ratio of the most important over the least important features to be of the least important feature over the most important features to be above 1.5%. This is a bit arbitrary, but it's what makes us stop at 18 features. So now I'm going to continue with the most important part of this presentation, that is model embedded methods, where we use the feature importance or define it while training the model. So a first approach that can be used is to impose L1 penalty while training, for example, a logistic regression. This enforces a certain sparsity in the vector coefficient that is output. So the optimization problem that we had when maximizing observed likelihood is slightly changed. Now we maximize the average log likelihood plus a penalty term that is a penalty constant multiplied by the one norm of the vector of coefficient beta. So this gives some results that I summarized in this slide. We can see that the number of non-zero coefficients decreases as lambda increases, and that it allows to moderately increase test set accuracy for lambda when it's between around 0.2 approximately. And then the test set accuracy and the training set accuracy both decrease. So now I'm going to talk about classification and regression tree. The idea of this is to build a decision tree to perform either classification or regression. This was introduced by Leo Brayman in 1994. And the classical algorithm that is as described is separated in two steps. First, we construct a maximal tree, and then we prune the tree to obtain an optimal tree. So the idea of building a decision tree to perform regression or classification is to start at the root of the tree with all observations of the training set and find the best possible split of the input space over one feature. That is, if the data is continuous, is to find a constant where we put the observations for which the J's feature is below this constant in one side of one sum of the root, and the observations where the J's variable is above this constant on the other side of the root that is in the other sum. The node that is below. The node has two children, and and the observations contained in the node are divided into the two children according to this splitting rule. And for the categorical, it's the same. We just define the subset of the categories that goes to one sum, and the other subset, the complement, that goes to the other sum. We repeat the operation on every new node until some stopping criterion is met. Usually it's don't split nodes with less than k observations. This is a typo, it shouldn't be children. It should be don't split nodes with less than k observations in it, for example. Usually, when it's for regression, we take 5 nodes, and when it's for classification, 1 node is fine because it's for the maximal tree, and then it's pruned to reduce the number of leaves. This is a sketch, so we see that we start with the root where all of the observations are, and then we define one splitting rule to separate in 2 groups for every node until we meet the stopping criteria. So in order to find the best split on every node, on each node, we have to define the cost of the split. For regression, this is defined by the intra-group variance of the 2 resulting children. So that is, if not T contains empty observations, we want to minimize the variation amongst the weighted average of the variation among the 2 children. That is the variation among the children in the left node, and the variation among the children among the observations in the right node. For classification, there is a similar weighted average that is given by the weighted average of the Gini index, which is given by the following equation, where we want to minimize the total variation among classes of one group. So to continue, here's the picture of the maximal tree obtained with the span dataset. We see that it's really big, and it has 166 leaves, and the test accuracy is not so good because there is a too big an overfitting basically that is arising because of these too many leaves, among which many leaves only have 1 node from the training set, which is very low, and that's why the maximal tree needs to get pruned to decrease the variance of its prediction. So in order to prune the maximal tree, we have there is a procedure that was described also by Brayman. This allows to reduce the number of leaves, which decrease variance, while maintaining training accuracy that is controls the bias of the model. If TT is a subtree of T with root T, which is a node of T, of the large maximal tree, we define the cost complexity measure for a given constant alpha greater than 0 by this formula, where the first term basically is the average classification error from the subtree, that is for nodes in the subtree TT, plus a penalty term that is given by the number of leaves. So the objective, as I said, is to decrease this cost complexity measure by decreasing as much as possible the error while making the number of leaves as small as possible. So given a maximal decision tree T, the minimal cost complexity measure for the pruning algorithm proceeds as follows. We define the effective alpha of the node T by the following formula. That is, we want the effective alpha is the alpha for which the cost complexity measure of the subtree is equal to the cost complexity measure of just pruning the tree, that is, of just leaving 1 node in the resulting tree. So this, by doing some algebra and equalizing this cost complexity measure to the one of the node is given by this, and this gives us the kind of metric that we can compute on every node of the tree, and we inductively prune the subtree corresponding to the smallest of this metric, because the smaller it is, the less important is the gain in accuracy, is the ratio of the gain in accuracy over the number of leaves that is induced by the subtree. So this is the procedure to prune the tree. We prune the tree by starting with the smallest alpha and continue. This graph shows us the way the training error increases when we prune more and more subtrees, with T0 being the initial maximum tree, and alpha k star being the alpha efficient corresponding to the node where the pruning occurs at step k. And this graph shows us the number of leaves that decreases very quickly and then stabilizes at a much smaller number. Finally, we have to see what is the optimal alpha k star, and we can, from this graph that is giving the train and test set error accuracy for different values of alpha, we see that we should prune until the alpha gets above an optimal alpha that is equal to 2 times 10 to the minus 3, which is corresponds to 65 pruning steps, and leaves an optimal tree with an improved accuracy of the test set compared to the 90% obtained with the maximal tree, and only 26 leaves, which makes it much smaller. So in terms of complexity, it's much better to compute predictions. This is the image of the optimal point tree with 26 leaves, but it's much smaller than the initial maximal tree. So from this CART model, there is several ways that we can evaluate feature importance. And then, for example, perform recursive feature elimination using the feature importance. The most heuristic way would be to look at the position where each variable intervenes, and to say the closer to the root, the most important is the variable, because each variable are put into competition at each node. So the fact that a variable intervenes among the first shows that it has gained it had the greatest reduction of error for the first node. So this shows that the variable was more important than the other. Similarly, we can look at the decrease in its heterogeneity due to splits on the variable divided by the total number of observations involved. This is another heuristic method that we show that I plotted below. And the less biased method is for each variable, compute the best surrogate split associated with the variable on every node and sum over all nodes. This is an approach that comes from the the idea of when you have missing values in a data set, you have to compute surrogate splits to, for example, if a node implies variable where there is a missing value for an observation, you want to have a surrogate split to be able to say in which children are going to go the observations with a missing value for this particular variable. And so the surrogate splits are put into competition, and the best surrogate split is chosen. But for each variable, we can compute the best surrogate split on each node and sum the cost complexity measure, the heterogeneity reduction due to this split over all nodes, and average it to obtain a better estimation for the importance of variable. So now I'm going to go on to random forest random inputs, which is the most subtle model that I'm going to present today. So the idea of random forest is to use cart models, but to train them on a large number of different bootstrap samples, and also so this includes the first random component, that is the bootstrap sample, the first theta, basically the theta i's in the sketch, and also to use also random subspace of features to train each particular tree that's reflected in the theta i's prime in the second line of the sketch. Then aggregate. So bagging is a contraction of bootstrapping and aggregating. This term was coined by Brayman, who introduced it in 1996. So to train a random forest, we draw Q independent samples from the training set, theta I, train the same model on each sample and aggregate the predictors. The aim is to reduce variance of the model and improve performance. This is part of the family of ensemble methods whose idea is to aggregate the same base learner trained over a different data set. In this case, it's different bootstrap samples drawn from the same data set. Other ensemble methods that are widely used include boosting, randomizing outputs, and random subspace. For boosting, the difference with bagging is that the samples are not independent of each other. Since from one sample to another, we increase the probability to select observations where the predictions were worse, and decrease the probability of selecting observations where we got a good predictions from the preceding model. Randomizing outputs consists to adding some noise to the output data. So in that case, it would be in classification not a good approach because it's not very adapted to add noise to classification. We could like perturb the binary column to some extent, but it would not be ideal. Random subspace is what I'm going to talk now. Was introduced by Ho in 1998. The idea is to randomly sample a subset of features and then aggregate the models that are trained on each different sample of features. So it is also an ensemble method. And so this, in addition to bagging, makes the trees even more different from one another and improve, and so it improves the aggregated predictor. Yes, so basically random forest combine two types of ensemble methods, bagging and random subspace, used on the one given model, that is cart tree. It is also important to note that usually with random forest, we don't prune the tree, we use maximal tree, but since they vary a lot from each other, there is not the overfitting that we have when training a single cart isn't an issue anymore. So the most crucial parameter when training a random forest is to choose the size of the number of features that we randomly draw for each tree. So usually in packages where random forests are implemented, the default parameter are square root of p for classification tasks and p over 3 for regression tasks, where p is the number of features. So for the span dataset, I just plotted below the test accuracy versus the number of features drawn. And it is interesting to note that for this particular task, to draw a single features for each tree gives the best results. That is that in this case, we train the decision tree on only one feature. That is that on every node, we just look for the best split involving this feature, and we don't put the splits from different features in competition as when there are more than one feature. And so the feature on which the splits are performed ultimately is purely random. There is no competition, which is kind of counterintuitive to think that it gives the best results. Usually, it's not. It's better to choose a subset with more than one feature. I'm going to explain now the out-of-bag error that comes when training a model with an ensemble method with bagging. So it allows to estimate generalization error without using test set. For each observation in the training set, we compute prediction using only trees fitted over a bootstrap sample, not containing this particular observation, and averaging over all observations, obtain an estimate for the generalization error. It is to note that the generalization error here was not computed with the whole aggregate predictor, but only with the aggregation of predictors not involving the observation where aggregation of predictors that haven't been trained on the observation where the error is being computed. So this is a quite good estimate for the generalization error, and it allows to estimate it while training the model without using a test set. And so it provides a way to avoid splitting the data set. Now I'm going to explain how to use out-of-bag error to compute feature importance. So we can feature importance measure with random permutation is a commonly used way to compute feature importance from random forest. We start by defining the feature importance of the variable xj as follows. So we compute the out-of-bag error for the corresponding tree. That is the tree corresponding to the bootstrap sample L. and we randomly permute the values corresponding to the JS variable in the complement of the bootstrap sample, where we are going to evaluate the error, which is the Outofbag error, that is the observations that are not in sample θ L. We compute predictions with the perturbed OOB samples, and the corresponding OOB error is given by the OOB LJ tilde, and the difference indicates how important XJ is for the prediction from 3L. That is, we see how much randomly permuting entries in the variable XJ on the complement of the bootstrap sample, where the error is being computed, impacts the error. That is, if the variable is important, it should greatly impact the error, and so this difference should be big. Whereas if the variable doesn't give any information to the tree, it should not impact it that much, and so the difference should be small. And we average over all bootstrap samples to obtain an estimate for variable importance. Usually, this approach should be due to the random aspect of this feature importance estimate, due to the random permutation of the variable entries. We need to repeat it a certain number of times to get a good estimate of feature importance. So on this slide, I put the final formula for the variable importance of variable k, and I also plot the most important features according to this particular method. We see that the standard deviation is quite small, so this indicates that we get a quite good feature importance estimate for at least for the most important features. Then we can use this feature importance measure to perform feature selection. So there are two possible situations in which we want to perform feature selection. First, we want to get as much possible information from the feature space about the target. That is, we want to keep all informative features to have the best interpretability as possible. This arises in the medical sector, for example, where we often have much more features than observations. And especially, for example, in when you have brain images and you want to estimate which regions of the brain react to a particular shock or stimulation, even if many regions react together and so are correlated and so are not all important to predict the shock or the stimulation, we want to keep them all because the goal is to really map which region of the brain are impacted by this particular shock. On the other hand, for prediction, we want to keep as few features as possible to make the model as simple as possible and as fast and reliable as possible. So I'm going to describe a procedure that is presented in a paper from 2017. First, there is a preliminary elimination. We fit a CART model on the rank of variables important to estimate the standard deviation. The idea being is that variable whose feature importance is less than the minimum standard deviation predicted should be eliminated because their feature importance basically vary more than their feature importance. it doesn't give a good it gives a good threshold to eliminate variables in this first step. So once we eliminate variables, we are left with m variables, and for interpretation task, we fit the same model on an increasing set of the most important features, and keep the set of features leading to the smallest out-of-bag error. Whereas for prediction tasks, we introduce variables sequentially similarly, but we only keep one variable if the decrease in the out-of-bag error is higher than the mean decrease over the previous variables. So it's a bit different. On the span dataset, the first step of the procedure is to keep only 34 features. And for interpretation, the second step preserves all of the features, remaining features, as we can see below. The best OOB score we obtain is with 34 features. Whereas for prediction task, the number of features we're left with is quite smaller, 25 features. I haven't included a graph to visualize this, but we're left with only 25 features. So it's quite smaller, and it allows to decrease the complexity of the model. To summarize, here this data set is we obtain a very good accuracy on the test set, whatever the model we are using. But we've seen that among the 57 features we had, only a few are useful, and it's interesting to see that the variable importance was very different from one estimate to another, and the widest variable importance we should consider in this presentation was the feature importance derived from random forest, which was really different from the one obtained with logistic regression coefficients or correlation, by point by serial correlation with staggered variables. Although random forest only moderately improved test accuracy. We also can note that random forest for prediction with only 25 features kind of reduced test accuracy. Even if it makes the model more explainable and more time complex and more easy and fast to compute predictions. So thank you everyone for your attention, and if anyone has a question,